So let's revisit whatever we have discussed so far. So far we have discussed that in supervised machine learning, when you're doing the linear regression problem, we have a data set D with a set of m data points, x i's and y i's, where I goes from 1 to m. And each of the x i's is a k-dimensional real vector. And each of the y's is a real scalar. And we also discussed that we have a basis function or a feature function or a feature like mapping phi, which is a mapping from k-dimensional real vector to some n-dimensional real vector. So it takes in the input xi's and produces a new representation phi of xi. And we discussed that the goal is to learn a functional mapping f with some learnable parameter w that takes in the input phi of xi and produces a corresponding target value in the data set yi as close as possible. And in the last part when we discussed processing interpretation of least squares, that we assume that yi is given by this functional mapping with some true parameter w. So we are not writing w star wmle right now. Just assume that there is some unknown parameter w which has some true value wmle or w star. So if you can compute this this value or the optimal value of w, then y is given by f of w. It takes the input phi of xi plus some small noise epsilon I. And if you remember the last lecture, we discussed that these epsilon i's are IID, and we discussed how important, the importance of this assumption, the IID assumptions. So if you remember, when we compute the likelihood and when we assume that each of these epsilon i's is independent, then the probability that the likelihood function is given by the probability of the errors or the probability of the data. And if each of these epsilon i's are independent, then the joint distribution of the errors epsilon i's is just a multiplication of the individual probability. So we had this nice formulation when we discussed the likelihood, the processing interpretation of least square. We have likelihood, we have WMLE is given by arg max over W, the likelihood of W. And the assumption of the independence, the IID assumption, gave us this nice formulation, this nice formula, I equal to 1 to m, P of epsilon I. That is, if the probability of the errors is very low, it means that the W is a good estimate, is good explaining our data. So which is simply equal to 1 to m, the conditional distribution of yi given xi and some parameterization parameter w. So w is not a random variable, it is just some variable whose value we just don't know yet, and this is a way to compute the value of w. So we assume that it's parameterized by some parameter w. So this IID assumption leads to this nice multiplication, and then we can take the log of this likelihood function, so which is same as minimizing the negative of the log likelihood, negative of the log of the likelihood function, right? Which results in summation, right? So it would be the negative of the log of P of yi given xi and parameter w. So we can open the log and all this multiplication will become in summation. And we showed you, we had proven in the last lecture that if these epsilon I has a Gaussian distribution, if this distribution is Gaussian, with mean 0 and some variance sigma square, then this leads to what is known as the least squares regression. So the least squares becomes a cost function, or this also, in other words, leads to minimizing the L2 norm of the error in the dataset or over the dataset. So this leads to the least square formulation, as well as the same as L2 norm squared. Which is norm of y minus phi times w square, which is also same as sum or I equal to 1 to m yi minus fw of phi of xi square. So that's why, since we are minimizing the squared errors, so each of these i's is resulting into epsilon I. So we are minimizing the squared summation of the errors. That's why it is known as the least squares. And it's also in vector form. It's also y minus phi times w L2 norm squared. That's why it is known as L2 norm squared error function, basically. So the Gaussian assumption, assuming that the noise has this normal distribution, leads to the least square, or in other words, the L2 norm squared error function. So likewise, so here, just for the sake of completeness, so here the phi is an n by n matrix where the ith row is phi of xi transpose, and this y is a vector of target values in the dataset. So this y is n m cross this phi is an m by n matrix. I'll just rewrite it. Phi is m by n matrix, where the ith row is given by this, and y is just m cross 1 vector, where the ith component is yi in the dataset. So we have shown that the normal distribution leaves us in the least squares. If we assume that these are normally distributed, then we have least square. And without proving today, we're just going to state this, which we'll prove later in this lecture. If we assume that epsilon I have a Laplacian distribution, so the good question is, what is Laplacian distribution? So let's assume there is a variable x, which is scalar. So x, if we assume that the x has a Laplacian distribution, so x PL, to denote that this is Laplacian, with some mean mu and some diversity parameter b. This mu is also known as the location parameter in the literature. It's also, like, you can compute that this is the expected value of the x, and this is also known as a diversity parameter. So this is given by 1 over twice of b times exp of negative of absolute value of x minus mu over b. So this is the Laplacian distribution of a variable x, of a random variable x, with mean mu and some diversity b. So if we assume that these epsilon i's have Laplacian distribution, then basically if we compute the WMLE in this case, so in this case WMLE, assuming that the epsilon i's are Laplacian with mean 0, this is arc max for W, the likelihood of the W, which is equal to pi of I equal to 1 to n P of epsilon I. So we are not going to prove it, but if you do the math, if you plug in this distribution of epsilon I with mean 0, what you get is this is equal to minimization of the L1 norm error over the dataset, which is equal to sum or I equal to 1 to m yi minus fw phi of xi and its absolute value, right? Which is same as the error EI. where EI, the error, is this term, right? So we have not proven it, but we'll be discussing later in the later part of this lecture that we'll be showing the math behind it. That if we assume that the epsilon i's are Laplacian, then WMLE is equal to minimizing the L1 norm of the errors over the data set, right? So here you can see we assume that the distribution is parameterized by this parameter W, right? So we are just considering that this W is some unknown parameter. So we are considering that the probability of Yi given Xi is parameterized by the parameter W, but W here is just an unknown variable whose value we would like to compute, and it is not a random variable. In other words, what does it mean? It means that we have no prior information on the values of W. Right. So we have no prior information as to what the ideal value of W should look like, right? Or the distribution of W should look like. So let's assume that W is some unknown parameter whose value we would like to find. And one of the natural ways is to find W is that, so for example, we consider likelihood function, that the likelihood of W is equal to the probability of the individual errors over the data set. So the larger the errors, you can say that if the errors are larger, then this is the W that doesn't explain the data set well. Whereas if the errors are smaller, then this is the W that explains the data very, very well, right? So obviously the natural choice of a W is the one that maximizes this likelihood function. And that this is what we exactly did in the last lecture. We just maximize this likelihood function to obtain the estimate of W, which we denote as WMLE. Right? But the underlying assumption is that W is 1. This is the only assumption. W is just some unknown variable. Whose value we need to find, right? What is value? It's not a random variable. It is not a random variable, right? It means that we have no prior information. But now the obvious question is that what if we knew that W, the learnable parameters W, have some known distribution, right? Before observing the data, what if you had some knowledge about what these parameters, what values these parameters should assume, right? So what if the question is 1. The first question is what if we have some prior information? Some prior information. And this prior information can be in the form of the distribution. So let's assume that our prior information is that W has some distribution P of W given some hyperparameter lambda and gamma, right? So what if we have some information that the W are coming from this probability distribution with some hyperparameters. So the lambda and gamma are not random variables, they're just some hyperparameters. So these hyperparameters actually control the sort of span or the weight or what the distribution should look like. So they control the distribution. So they're the hyperparameters of the distribution. And now, since we have this information, the next obvious question is, what can we do about it? Right? So the next obvious question is there a way to incorporate this prior information into our likelihood formulation or in the optimization problem. So earlier the optimization problem is, so as you can see here, we are maximizing this likelihood function. So this is an optimization problem, right? So now the obvious question is, can we have an optimization formulation that takes in this prior information over the parameter W and somehow combines it with the likelihood function, right? Can we combine with the, so taking this prior information and combining it, so I'm just denoting as some symbol, right? So can we combine this with the likelihood function, right? P of yi given xi comma w. So now you can see we are not writing a semicolon over here. Earlier we had semicolon to denote that w is just a parameterization parameter. It's not a random variable, but currently we have replaced this semicolon with this comma, which means that now we have some prior information over this parameter w, and this is that prior information. And now, given the prior distribution and the likelihood function, is there a formulation where we can plug in the two or combine the two in some fashion, and which leads to an optimization problem that we can actually solve to get a better estimate, which takes our prior information into account, to get a better estimate of the parameter w, which will result as w new, which is not equal to WMLE. So can we find this optimization formulation which gives us this new better estimate? Why is it better? Because for obvious reason, it is taking the likelihood into account. It is also taking the prior information into account. So combine the two, can we obtain a new w such that when a new variable x hat comes, we can plug it in the function. To get the resultant value y hat. Sorry, I shouldn't have the equal sign over here. So for the new variable x hat, can we plug in the function using the w new and obtain a resultant value y hat? Can we do this, right? And obviously the answer is yes, and that's why we are having this lecture, right? So now in the next part of the lecture, we'll show you exactly how to do this.